Have you ever wondered how Netflix knows the next show you'll binge watch? Or how banks flag a suspicious transaction in seconds? The secret lies in predictive modeling, one of the most powerful applications of data science and AI. In this video, we'll break down what predictive modeling is, how it works, and why it matters in today's world. Imagine trying to navigate an ocean. Looking at your wake only tells you where you've been. What if you had a tool that analyzed currents and wind to chart a probable course forward? That's predictive modeling. It's a statistical technique that goes beyond the rearview mirror. It uses historical data and sophisticated algorithms, like machine learning, to forecast future outcomes, trends, and probabilities. The process begins with data: past sales figures, customer clicks, sensor readings. This historical data is the fuel for a statistical algorithm that learns the underlying patterns. Instead of just telling us what happened, which is descriptive analytics, predictive models use these patterns to make an educated guess about what might happen next. It's the crucial shift from being reactive to proactive. You experience this every time you open Netflix. It's not random. A predictive model analyzes your viewing history, genres you prefer, and your ratings. It compares your behavior to millions of users with similar tastes. The result is a personalized homepage with recommendations you're highly likely to enjoy, keeping you engaged and subscribed. It's a cornerstone of their business. In finance, predictive modeling is a frontline defense against crime. Banks build models that learn the rhythm of your financial life, your typical purchase amounts and locations. When a transaction suddenly breaks this pattern, like a large purchase thousands of miles away, the model flags it in real time. This can trigger an instant alert or a card freeze, stopping fraud before significant damage is done. In healthcare, the impact is profound. By analyzing a patient's health records, genetics, and lifestyle, models can identify individuals at high risk for chronic diseases like diabetes, often years before symptoms appear. This foresight allows doctors to move from treatment to prevention, recommending personalized changes or therapies early. It's a shift towards proactive medicine that can save lives. Retailers also use this technology. A model can analyze purchasing frequency and recent activity to calculate a churn score, the likelihood a customer will leave. If a loyal customer becomes inactive, the model flags them as a high churn risk. This can automatically trigger a targeted retention campaign, like a personalized discount, to win them back before they're gone. So where does predictive modeling fit? Descriptive analytics looks at the past. We sold 500 umbrellas last month. Predictive analytics forecasts the future. Based on weather patterns, we'll likely sell 800 next month. It provides the forecast. Then, prescriptive analytics suggests an action. To meet this demand, order 300 more umbrellas. Predictive modeling is the vital bridge between understanding what happened and deciding what to do next. Now, let's understand how predictive modeling works step by step. This isn't a single magic trick, but a structured, methodical process. Think of it as a recipe for making predictions, where every single ingredient and every step is crucial for the final outcome. While the terminology might sound complex, the underlying logic is surprisingly intuitive. We're essentially teaching a computer to learn from the past to make informed guesses about the future. Let's break down this journey into 6 core stages. 1. Collect data. Everything begins with data. We start with historical datasets, which are the bedrock of our model. This is the raw material from which our insights will be forged. This data can come from anywhere: customer purchase histories, patient medical records, financial transaction logs, website click streams, or even sensor readings from industrial machinery. The core principle is garbage in, garbage out. The quality and quantity of our initial data directly determine the potential accuracy of our model. A model trained on sparse, irrelevant, or biased data will inevitably produce poor predictions, no matter how sophisticated the algorithm is. That's why data collection is a critical first step. 1. Pre-processed data. Raw data is almost never ready to be used. It's often messy, incomplete, and full of inconsistencies. This is where pre-processing or data cleaning comes in. Data is cleaned, missing values are handled, and new features are engineered. For instance, we might have to decide how to fill in missing age information for some customers. Do we use the average age or a more complex method? We standardize formats, ensuring New York and NY are treated as the same location. We also perform feature engineering, which is the creative heart of this step. It's about creating new, more powerful variables from the ones we already have. For example, from a customer's date of birth, we can engineer their age. From a series of purchase timestamps, we can engineer the average time between purchases. This step transforms our raw data into a clean, structured, and feature-rich dataset, perfect for training a model. 1. Choose a model. With our data ready, we need to select the right tool for the job. There's no one-size-fits-all algorithm. Depending on the problem, we may use regression, decision trees, or even neural networks. If our goal is to predict a continuous number, like a house price or future company revenue, we'd likely choose a regression model. If we're trying to predict a category, for example, whether an email is spam or not, or if a customer is likely to churn, we might use a classification model like a decision tree. For highly complex problems with vast amounts of data, like recognizing objects in images or understanding human language, we might turn to the power of neural networks, which are designed to mimic the human brain's ability to find intricate patterns. The choice of model is a crucial trade-off between performance, complexity, and how easily we can interpret its results. 1. Train the model. This is the learning phase. The algorithm learns from patterns in the training data. We feed our pre-processed data into the chosen model. The algorithm then iteratively adjusts its internal parameters to minimize the difference between its predictions and the actual outcomes in the data. It's like giving a student a set of practice problems with an answer key. They attempt a problem, check their answer, see how far off they were, and adjust their approach to get closer to the correct answer next time. This process is repeated thousands or even millions of times until the model's error rate is as low as possible, and it has become an expert at finding the relationships hidden within the data. 1. Validate and test. Once training is complete, how do we know if our model is actually any good? We can't just trust its performance on the data it learned from. That would be like giving a student the exact same questions on the final exam that were on their practice sheet. Instead, the model is tested on new unseen data to ensure it performs well in the real world. Before training even began, we set aside a portion of our data, typically around 20%, called the test set. The model has never seen this data before. We feed the test data into the model and compare its predictions to the actual known outcomes. This gives us an unbiased evaluation of its accuracy. If the performance is good, we can be confident in our model. If not, we go back, tune our model, or even choose a different one and repeat the process. 1. Deploy the model. Finally, the model is ready to leave the lab and go to work. It's integrated into apps like a credit scoring system or a recommendation engine. This is where the model starts providing real value. It could be a fraud detection system flagging suspicious transactions in real time, a recommendation engine on a streaming service suggesting your next favorite movie, or a predictive maintenance model in a factory forecasting when a machine part will fail. But the work isn't over. The world changes, and so does data. A model's performance can degrade over time in a process called model drift. Therefore, deployed models must be continuously monitored. If performance drops, the model is retrained on new, fresh data, ensuring it remains accurate and relevant, making this a continuous, cyclical process of improvement. Think of it like training a student. First, they gather all the textbooks and past exam papers. That's data collection. Then, they organize their notes and create flashcards to make the information easier to digest. That's pre-processing. They do practice problems where they can check the answers, learning from their mistakes. That's training the model. To see if they are truly ready, they take a mock test with new questions they've never seen before. That's validation and testing. Finally, they take the real exam and apply that knowledge in their future career. That's deployment. And just like a professional must keep learning to stay current in their field, the model must be monitored and retrained to remain effective. The world of predictive modeling is rich with a diverse toolkit of techniques. There isn't a single master key. Instead, data scientists select the right tool for the specific problem they're trying to solve. Let's explore some of the most fundamental and powerful methods used today. We begin with regression models, the bedrock of predictive analytics. Linear regression is used to predict a continuous numerical value. Think of predicting a house's price based on its size and location, or forecasting a company's quarterly revenue. It works by finding the straight-line relationship between variables. On the other hand, logistic regression is your go-to for predicting a binary yes or no outcome. Will a customer click on an ad? Is a transaction fraudulent? Logistic regression calculates the probability of a specific outcome, making it invaluable for classification tasks. Next are decision trees and their powerful evolution, random forests. A single decision tree is highly intuitive, mimicking human decision-making with a series of if-then questions. It's easy to visualize and understand, which is why it's known as a white box model. However, a single tree can sometimes be too specific to its training data. That's where random forests come in. This technique builds an entire forest of individual decision trees and combines their outputs. By averaging the predictions of many diverse trees, it dramatically improves accuracy and prevents errors, making it a robust choice for many real-world problems. When your data has a time component, you turn to time series models. These are designed specifically to analyze data points collected in chronological order, identifying trends, seasonality, and cycles. Classic models like ARIMA are statistical workhorses, excellent for capturing patterns in stable data. For more complex, real-world business forecasting, models like Profit developed by Facebook are incredibly effective. They are designed to automatically handle challenges like holidays, missing data, and abrupt trend changes, making them perfect for sales forecasting, inventory management, and predicting website traffic. For the most complex challenges, we have neural networks, the engine behind the deep learning revolution. Inspired by the structure of the human brain, these models consist of layers of interconnected nodes that can learn incredibly intricate patterns from vast amounts of data. They excel where traditional models struggle, especially with unstructured data. Neural networks are what power image recognition in self-driving cars, allow voice assistants like Siri and Alexa to understand your speech, and enable real-time language translation. Ultimately, there is no single best technique. The choice depends entirely on the problem you're solving, the nature of your data, and your need for interpretability versus raw predictive power. A simple regression might be perfect for one task, while a complex neural network is required for another. The art and science of predictive modeling lie in understanding these trade-offs and skillfully selecting and tuning the right model for the job. Predictive modeling powers some of the most impactful innovations today. E-commerce, predicting customer churn and recommending products. Finance, credit scoring and fraud detection. Healthcare, predicting diseases like diabetes or heart failure. Manufacturing, predictive maintenance of machines to avoid costly breakdowns. The possibilities are endless, from predicting traffic congestion to forecasting energy consumption. To sum up, predictive modeling helps us look into the future by learning from the past. With the rise of AI, AutoML, and explainable AI, predictive modeling is becoming more accurate and accessible than ever before. If you found this video helpful, Don't forget to like, share, and subscribe to The Data Key for more deep dives into data science and AI. And let me know in the comments if you'd like a hands-on tutorial with Python for predictive modeling.